Hello viewers, I hope you are doing well. In this new video, we will be discussing few simple but very important questions and their answers in brief. By this, you will learn how to write answers briefly, concisely, and succinctly. So this is about introduction. I advise you one more thing. The commonly used constants in chemical calculations, you should know their meaning, their digital values, and units as well. The first question reads, write Schrodinger wave equation for a tiny particle of mass m freely moving in a one-dimensional box, bounded by walls of infinite height, that is potential energy level. This is a very, very important question, very often asked in examinations. The answer reads like this. For a tiny particle of mass m freely moving along x direction in a 1D box of width a, shown in figure 1, the Schrodinger wave equation in x coordinate is written as follows. See the figure. The potential well has been shown. Its width is a, beginning from 0, shown along x direction. On the walls and outside the walls, potential is infinite. Wave function is 0. Within the box, wave function is not 0. Potential is uniform throughout. It means no potential barrier exists. For mathematical easiness, we have set Vx equal to 0. The equation is this: d2 psi upon dx2 plus 8 pi square m upon h square e minus v psi equal to 0. In another form, this can be written using h upon 2 pi, replacing by h cross. The letter-like symbol h cross is called reduced or modified Planck constant, also called Dirac constant. It is the same as h upon 2 pi, and its numerical value is 1.055 into 10 to the power minus 34 joule second. Because the particle is freely moving in the box, forth and back between x greater than 0, less than a, with a speed u, its potential energy Vx is treated as uniform throughout. That is to say, Vx is constant at all points within the box. In other words, while moving within the box, the particle does not experience any potential energy barrier. For convenience, mathematically, Vx is set equal to 0 because differentiation of constant is 0. In the above second order differential equation, psi x is the state wave function and E is the total energy of the particle. It means E total equal to kinetic energy, AE plus potential energy, which is 0. Therefore, it is equal to mu square by 2, u is velocity. Note that psi x is 0 when x is less than 0 or equal to 0, greater than a or equal to a. Because 1D box is bounded by wall of infinite height. The particle cannot surmount these walls and therefore it will remain confined within the box. On the two walls, x equal to 0 and x equal to a, and outside the box, that is x less than 0 or greater than a. Wave function psi x becomes 0 because the particle cannot be found there. Thus, equation 1 can be written ignoring the potential energy term Vx. It becomes d2 psi x over dx square plus 8 pi square me over h square psi x equal to 0. Solution of equation 2 reveals the existence of quantized energy states defined by the expression En equal to n square h square divided by 8ma square, where n is the quantum number having values 1, 2, 3, etc. Note that the value n equal to 0 is not allowed, because if we accept this value, it means the wave function becomes 0, which means the particle exists nowhere. Therefore, n equal to 0 value is omitted. Also note that for a box of very long width, x approaching infinity, quantization of energy state disappears because gap between consecutive states is almost 0. Solution of equation 2. So we have written equation 2 here again, and for simplicity, the constant term 2me over h square has been collected as k square. So equation becomes in the form of 2c. It is an ordinary second order differential equation. It has many solutions. One of the solutions is of the form noted below. Psi x equal to a cos kx plus b sin kx. In equation 3, both a and b are arbitrary constants. It means if we want to solve this equation 3 so as to determine the value of wave function, we have to eliminate one of these two constants, a and b. Then only one constant will remain, and it has to be evaluated. And there is very important step lies here, how to eliminate one of the arbitrary constants. For that, we will use the concept of limits. What are the limits? When x is a or more than a, or when x is 0 or less than 0, wave function psi vanishes. It means psi x becomes 0. This is the condition we will apply to solve this equation number 3. Applying that condition, we can write equation in the form of equation number 4, and equivalently equation number 5. These two are equivalent equations written in different parts. So one of the solutions is psi x b sin kx equal to 0, or psi x equal to 0 equal to b sin ka, applying the limits. It means ka equal to n pi, or k equal to n pi over a. We have done a very important step. We have evaluated k. It means we have gone a few steps ahead. The constant n is relevant quantum number, as said earlier, having values 1, 2, 3, etc. Hence, the allowed solution of equation 2c is psi x are same as psi m equal to b sin kx, replacing k by n pi by a. We can write psi x or psi m equal to b sin kx or b sin n pi x over a. And remembering that k square is n square, pi square over a square, also equal to 2me over h cross square. We can put the value of k, and thus we have evaluated energy En equal to n square h square over 8ma square, where a is the width of the box, m is mass of the particle, n is quantum number, h is Planck constant. Question number 11 is for energy. Normalization of wave function. The particle must be found within the box, between the limits x equal to 0 to x equal to a, not beyond. Obviously, the total probability of finding the particle as given by the Born's interpretation of wave function must be 1. Mathematically, it can be written limits x 0 to x1 psi square dx equal to 1. Now we can put the value of psi here and integrate the equation. On integration, we evaluate b as under root 2 over A. Having determined the constant B, normalization constant, we can write the normalized wave function as follows. Psi nx equal to under root 2 by A multiplied by sin n pi x over A, where n is the quantum number, integral value. Quantized energy states. For equation 11, or a tiny particle of mass m in 1D box of its shape, energy is proportional to n square. Obviously, E4 ratio E3 ratio E2 ratio E1 equal to 16 is to 9 is to 4 is to 1. Hence, energy states are discrete and quantized. We can say that. A numerical example. For electron moving in a 1D box of width 1 nanometer, we can calculate E1 n square h square over 8 m square, putting the value of n equal to 1, h, m, and a. We can evaluate E1 as about 38 electron volt. On this ground, E2 will be 4 times this value, E3 will be 9 times this value, E4 will be 16 times this value. In the following graph, the wave function, probability function, nodes along with energy values are shown. See, in this vertical graph, the quantum numbers are taken 1, 2, 3, and 4. Psi is plotted against x. For the first energy state, there is no node. For the second, there is one node. For the third, there are 2 nodes. For the fourth, there are 3 nodes. In this counterpart, psi square has been plotted against A, and we have shown that there exist discrete energy states. It means when the particle is moving in 1D box having potential walls, then energy states are quantized. If the particle is freely moving, no limits, no walls, then energy states are not quantized. Thus, we have completed one question. The second question reads that given below are some solutions of Schrodinger wave equation, that is psi x value. That is psi x equal to x square, sin x, e power x, e power minus x, e power minus x square, and tan x. We have to select which of these values show acceptable psi x. We know the acceptable values of wave function are those values which are continuous, finite, and single valued at all points within the range. Thus, both psi x equal to sin x and psi x equal to e raised power minus x square are accordingly acceptable wave function solutions. Why? For all values of x, psi x equal to sin x is finite because psi x values range from -1 to +1. Sin x value. Likewise, for psi x equal to e raised power minus 2x square, as x approaches plus minus infinity, psi x approaches 0, finite value. Hence, psi x equal to e raised power minus x square is also an acceptable wave function. Both psi x equal to e power x and psi x equal to e power minus x are not acceptable because psi x approaches infinity as x approaches infinity, or x approaches minus infinity. Note that the variable x can be anything between minus infinity to plus infinity. So psi x can be infinity for both e power x and e power x square. Therefore, these values of wave functions are not acceptable. The function psi x equal to tan x is also unacceptable because tan x is pi by 2, psi x approaches infinity, infinite. Question 3. Write first, second, and seventh postulates of quantum mechanics. First postulate of quantum mechanics, that is the wave function postulate. The physical state of a system is defined by a state function or wave function, psi, say. Thus, for a particle of tiny mass m moving along x coordinate, we can describe the state as psi xt, where both x and t are the variables which define the state of the system under study at particular time t. Any acceptable wave function psi must be continuous, finite, single valued at all points, and double differentiable. The integration of psi square dv or psi multiplied by psi star dv, where dv is volume element, must give 1. However, if the wave function psi contains imaginary term I, instead of taking psi square, psi multiplied by its conjugate, psi star, this ensures elimination of imaginary I. Now suppose that we are dealing with a two-particle system, that is the electron and proton of hydrogen atom. The state can be written as psi equal to f x1 y1 z1 x2 y2 z2 t, where x, y, z are coordinates of both particles as indicated by appropriate subscripts 1 and 2 respectively. For an n-particle system, the equation governing the time dependence of the system is the following. Summation is from I equal to 1 to n. H cross square over 2 mi d2 psi over dx1 psi dx1 square plus d2 psi over dy2 square plus d2 psi over dz1 square plus potential term v xi yi zi t psi equal to I h cross d psi over d2 dt. So this is the expression for a system having n particles. In this second order differential time dependent equation, mi is the mass of ith particle, v is the potential energy. Equation contains the first derivative of the state function psi with respect to time t, that is d psi over dt. Therefore, a single integration of equation with respect to t yields psi and introduces only one arbitrary constant of integration c. Hint is given here. Integration of k dx, where k is some constant, yields kx plus c, where c is some arbitrary constant called integration constant. If the state psi at initial time t0 is known, the arbitrary constant c can be evaluated. Once we have known the initial state of the quantum mechanical system, its future state can be predicted. However, in quantum mechanics, every result is based on probability rather than certainty. This is the major difference between quantum mechanics and classical mechanics. Second postulate of quantum mechanics, it is called the wave function is acceptable provided that psi xt and its first derivative and second derivative are continuous, finite, and single value for all values of x. Also, the wave function psi xt is normalized. The meaning of normalization is given here. Integration limits are minus infinity to plus infinity. Psi xt multiplied by psi xt dx equal to 1. Notice that where the function psi contains an imaginary function, that is psi equal to e raised power I m cube, like this, it must be multiplied by its complex conjugate psi star equal to e raised power minus I n cube. So that the imaginary I value can be eliminated. I is under root minus 1. Hint is given here. Suppose psi value is e raised power minus I n cube. Then it has to multiply by e raised power I n cube, so that e power 0 becomes 1. But the wave function is real, no need to take complex conjugate of psi. For example, integration between limits minus infinity to plus infinity, psi xt into psi xt dx equal to 1. Seventh postulate. The wave function psi xt is the solution of time-dependent Schrodinger equation h psi xt equal to I h cross d psi over dt, where I is under root minus 1. Here h is the Hamiltonian operator, also called total energy operator, that is plus kinetic energy operator T plus potential energy operator V. Also h is minus h square upon 8 pi square 1 del square plus V, where Laplacian del square equal to d2 upon dx2 plus d2 upon dy2 plus d2 upon dz2. Differentiation twice. Let us proceed to fourth question. Write third and fourth postulate of quantum mechanics. Third postulate of quantum mechanics, concept of Hermitian operator. The physically observable quantity, that is energy, momentum, electron cloud, density, etc., can be represented by Hermitian operator. Let us consider the following expression. Integration psi I star operator A psi j dx equal to integration psi j within bracket operator A psi I star dx. If this condition holds, then the operator is said to be Hermitian. In other words, an operator is said to be Hermitian when it can be flipped over to the other side if it appears in an inner product. They always have real value, eigenvalues, not involving I. Since the eigenvalues of the quantum mechanical operator correspond to measurable quantities, the eigenvalues must be real. It is postulated that all quantum mechanical operators that represent the dynamical variable are Hermitian. An example is the Hamiltonian operator H. Fourth postulate of quantum mechanics, that is experimental observable of dynamical variable postulate. Consider the following expression. The allowed values, the eigenvalues of an observable parameter A are AI in the operator expression. Operator A psi I equal to AI psi I. Give few examples of eigenfunction, eigenequation and eigenvalue. Answer. If a function f upon being acted by an operator gives the same function multiplied by some constant, it is prescribed as an eigenfunction. Example 1. Suppose the eigenfunction is e power 2x and operator is d by dx. Upon operation, we get the same function, that is e power 2x multiplied by 2. Here 2 is the eigenvalue. Another example is cos kx acted upon by d2 upon dx2. It produces minus k square cos x. It means here minus k square is the eigenvalue. Similarly, in the expression h psi equal to e psi, e is the eigenvalue, psi is the eigenfunction, h is the operator, and this expression is called eigenequation. Hamiltonian operator is described earlier. Another example, suppose you have a function cos 2 pi ft. If we differentiate this twice, we get minus 4 pi square f square cos 2 pi ft. It means here the eigenvalue is minus 4 pi square f square. Question 6. So that psi cos ax cos by cos cz is an eigenfunction of the Laplacian operator and calculate its eigenvalue. In Cartesian coordinate system x, y, z, the Laplacian operator is defined as d2 upon dx2 plus d2 upon dy2 plus d2 upon dz2. Differentiation twice means d2 function over dx2 means d by dx of what? D function f dx. Now the same formula is used. We first differentiate cos ax cos by cos cz with respect to x to get minus a sin ax cos by cos cz. Differentiating again, we get minus a square cos ax cos by cos cz. Following the same principle, we will differentiate the expression, the function, with respect to x, then with respect to y, then with respect to z. And finally we get multiplier factor minus a square plus b square plus c square. This is the eigenvalue. And the same function results, that is cos ax cos by cos cz. It means we have finally eigenvalue into eigenfunction. Question 7. Write equation of a straight line. The graph is shown here. X is the independent variable, y is dependent variable. There is no intercept, and the gradient is theta, which is less than 90 degree. It means the slope is positive. Slope m equal to tan theta, and expression is y equal to mx plus c. The second B graph, the difference is intercept is non-zero, intercept is c, positive value. Slope is positive, as earlier. In the third graph, slope is negative, intercept is positive. In the fourth, intercept is negative, slope is positive. So we must know how to interpret the various types of graphs. We have also put some other equations of straight line. One more expression. Question 8. Write total differential of a function fxy. df, total differential of the function, is given by del f upon del x and holding y dx plus del f upon del y holding x dy. Question 8b. Explain the concept of partial differentiation and write about Euler-Sackley proof. The concept of partial differentiation is very much used in the study of thermodynamics. Let us consider a situation in which the change in the state property z shape depends on two independent variables x and y shape. Total differential of z called an exact differential dz is given by dz equal to dz upon dx holding y dx plus dz upon dy holding x dy. In this expression, the complete differential dz is equal to the sum of two partial differentials. That is the rate of infinitesimal change in z with respect to infinitesimal change in x at constant y multiplied by the infinitesimal change in x. Okay? dz upon dx holding y dx plus similar partial change in z with respect to y at constant z. That is dz upon dy holding x dy. The order of change with respect to variable x and y makes no difference so long as the function is a state function. That is why the total differential dz is called as a z differential. It means dz can be written as equal to dz upon dxy dx plus dz upon dyx dy, also dz upon dyx dy plus dz upon dxy dx. For example, for an ideal gas, entropy S is a function of independent variable, temperature and pressure, or temperature and volume. Mathematically, S is a function of T and T, or S is a function of T and B. Likewise, internal energy is a function of T and P, or E is a function of T and B. Here we have written equivalent expressions for ds or dE, four different expressions with respect to two independent variables. Considering equation 1 again, you can have dz upon dx constant y as mxy, dz upon dy constant x as nxy. It means we can write the same expression in a different manner. Taking next second derivative, d2z over dy dx equal to d2z over dx dy. Hence, d2z over dy dx equal to del m over del y whole dx, and d2z over dx dy equal to del m over del x whole y. Here it has been assumed that mxy and nxy have continuous derivative. From equation 9 we obtain del m over del y holding x equal to del m over del x holding y. This is expression number 10. This is called Euler's reciprocity relation, and it corresponds to an exact differential. Then we have a very important rule, cyclic rule or chain rule. Let us consider the function dz equal to dz over dx at y constant dx plus dz over dy at x constant dy. Assuming that dz is constant, it means dz is 0. We can derive dz over dx holding y into dx over dy holding z into dy over dz holding x equal to -1. This is a very important rule, very often used in thermodynamics. Question 9. Explain Zeeman effect and Stark effect. An electron is associated with orbital and spin angular momentum vectors. The orbital angular momentum vector L is given by L equal to h cross under root L plus 1. L is 0 for s orbital, 1 for p orbital, 2 for d orbital, and 3 for f orbital. Similarly, for electronic spin vector S has h cross under root s plus 1, where s equal to total number of unpaired electrons multiplied by half. By virtue of their electrical charge, electron is associated with magnetic moment mu, given by equation mu equal to minus G E mu Bs. Here G is called electron G factor, or Landage spectroscopic splitting factor of numerical value 2. Mu V is Bohr magneton unit. S is the spin vector. When an external magnetic field is exposed, the spin vector is split into two components. one corresponds to anti-clockwise spin, another one corresponds to clockwise spin. We have two energy states separated by delta E equal to gamma H cross B. Dutch physicist Peter Zeeman in 1896 had discovered a phenomenon which causes the splitting of the spectral emission line into two or more slightly different frequencies, and the light source is placed in a static magnetic field. This is called Zeeman splitting. The effect of external electric field on the spectral lines of emitting atom and molecule, resulting into the splitting of frequency, is called the Stark effect. German physicist J. Stark, 1913. This is the end of this video. We have attempted few fundamental questions, how to write their answers briefly, and I hope it will be useful for you. Maybe you require 2-3 more readings. For biology group students, they should not be afraid of this, because very simple mathematical relations are used, and every student is expected to know this much. Thank you very much. Thank you once again.